In order to understand this chapter well, you're going to have to be very proficient at drawing Lewis structures. Now, you did draw some Lewis structures in your first year course, but I'm going to show you a new method today that is going to be much more versatile in allowing you to draw much more difficult structures than you were drawing in your first year course. Okay, so I have a list of steps up here, and I'm going to go through the list of steps just to make sure that you can read everything I've written. And then we're going to spend lots of time going through examples so you can see exactly how to make this work. Okay, so when you draw a Lewis structure, the first thing that you want to do is count the number of valence electrons that are available for bonding in all of the atoms together. Then you're going to determine the central atom. For most of the examples that we're going to be doing, the central atom is going to be fairly obvious. You do want to look for symmetry, and if you have to make a choice, the least electronegative atom tends to be the central atom. Now, we did talk about electronegativity in your first year course. Electronegativity has to do with how strongly an atom tends to pull electrons towards itself. And if you will recall, fluorine is the most electronegative element on the periodic table. And so increasing electronegativity, it goes up and it goes to the right, so that you end up here with fluorine as the most electronegative, okay? Once you've determined what your central atom is, then you're going to connect everything else with single bonds to your central atom. You're going to put all of the remaining electrons from this total as lone pairs. If you've got too many, then you're going to turn your lone pairs into double or triple bonds to give every atom an octet. If you don't have enough, then you're going to add lone pairs to your central atom. Okay, now I'm sure that right now that probably doesn't make a whole lot of sense, but I'm going to go through it step by step and show you exactly what it means. But like I said, I wanted to just go through with you what it said in case you wanted to pause the video and copy it down. That's up to you whether you do that or not, of course. So the first few examples I go through are going to be very, very simple, so that you can start to get your mind warmed up and understand what we're doing here. So let's look at a fluorine, just a straight diatomic atom. If you look at the periodic table, you should see that fluorine has 7 valence electrons. And so I'm going to have 7 valence electrons times 2 is going to give me 14 valence electrons. So, I mean, I only have 2 fluorines, so obviously they've got to be bonded together. So I'm going to bond them together. So there I've used 2 electrons. And I'm going to put all the remaining electrons as lone pairs. So I'm going to count them as I put them on and see what I end up with. So I have 2, 4, 6, 8, 10, 12, 14. Okay? That worked out well because I have a single bond and I used up all the electrons that I had, and everybody's got an octet, everybody's happy. Okay? So fluorine's pretty simple. All right? Let's look at oxygen. We did this example the other day, and so we already know what it looks like, but for the sake of how to draw the Lewis structure, let's just go through this one as well. Oxygen has 6 valence electrons. I have 2 of them, and so that's going to give me a total of 12 valence electrons. So again, I just have 2, so obviously they're going to be bonded together. So there I've used 2 valence electrons. So now I'm going to put the remaining electrons as lone pairs. So I've got 2, 4, 6, 8, 10, 12. I can't put another one up here because I'm going to go over 12. So what am I going to have to do? Well, I'm going to have to turn one of these lone pairs. I'm going to have to put it over here, and I'm going to have to share one of them instead. So now let's see what I've got. I made a double bond, so now I've got 2, 4, 6, 8, 10, 12 valence electrons. So the oxygen molecule is going to have a double bond in it, okay? What about a nitrogen molecule? What's that going to look like? Well, each nitrogen has 5 valence electrons, and there are 2 of them, so that's going to give me a total of 10 valence electrons to use, okay? So since I only have 2 atoms, I'm going to go ahead and combine them together with a single bond. So there's 2 electrons. going to start putting the rest as lone pairs. So I've got 2, 4, 6, 8, 10. Well, obviously I already have a problem. I think you probably could tell that was going to happen based on what I'd already done previously here. So I've got 10. I don't have this guy nearly full with the octet rule, so let's start taking some of these off and sharing them. So let's take this one off and make a double bond. What's that going to give me? 2, 4, 6, 8, 10, but this nitrogen still does not have an octet around it, and so I'm going to take one more electron pair off, and I'm going to share that in the middle instead. So I'm going to put this lone pair over here just so it's a little more balanced. So now I've got 2, 4, 6, 8, 10. Now I've got all 10 valence electrons accounted for, okay? So my nitrogen molecule has a triple bond in it, all right? How about NH3, okay? Well, nitrogen has 5. Each hydrogen has 1, but there are 3 of them, so that gives me a total of 8 valence electrons. All right, so let's see how this is going to work. Nitrogen is going to be the least electronegative, or it's going to be the only possibility actually, because hydrogen can only have one thing bonded to it. It can only have, it doesn't have an octet around it, if you will recall, because in order to look like the nearest noble gas, it's going to look like helium, so it can only have a total of 2 valence electrons. So the nitrogen is the one that everything has to be bonded to. So nitrogen is going to be my central atom. I'm going to bond each hydrogen to it. So there's 2 electrons, there's 4 electrons, there's 6 electrons, and I'm going to put the remaining one as lone pairs. So there's 8 valence electrons. The nitrogen has an octet. Each hydrogen has 2. Everybody's happy. So again, ammonia is a relatively simple one. All right, let's look at COCl2. Okay, COCl2. Carbon has 6 valence electrons. I'm sorry, that's not right. Let's try that again. Carbon has 4 valence electrons. Oxygen has 6 valence electrons. Each chlorine has 7, and there are 2 chlorines. So that's going to give me 14 plus 4 is 18 plus 6 is going to give me 24 valence electrons. Okay, so 24 valence electrons to work with. Almost always you're going to find that carbon is going to be your central atom. It's very, very versatile. It can have 4 things bonded to it. And so this is just very often used as a central atom. So if you see something like this, almost for sure it's going to be, carbon's going to be in your middle. Okay, so here's my carbon. I'm going to bond 1 oxygen. There's 2 electrons. Another oxygen is 4 electrons. And a chlorine bond. I did that backwards, didn't I? Let's put 2 chlorines on there instead so that we're obeying the formula that I put up there. Okay, so 1 oxygen. There's 2 electrons. I've got 2 chlorines. So I've got 2 electrons and 2 electrons. So I've used 6 so far. Okay, so 6, 8, 10, 12, 14, 16, 18, 22, 24, 24, that's all I have. I don't have any more electrons to use, so I'm going to have to start double bonding because I don't have an octet around either one of these guys yet. Where's the double bond going to go? Well, the chlorine, if you, again, recall from your first year course, chlorine really only prefers to have 1 bond. And so the oxygen prefers to have more bonds than that. And so we're going to put a double bond here and see where that gets us. Okay, so now I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, 24 valence electrons. So that worked out right. We have a double bond here and 2 single bonds there. Okay. What happens if you have an ion? Because you are going to be asked to draw some dot structures and determine hybridization for some ions. So I'm going to make some more space here without erasing all of my steps. Let's say that I have a hydroxide ion, OH minus, okay? So my oxygen is going to have 6 valence electrons. My hydrogen is going to have 1 valence electron, and because it has a negative charge on it, that means it's going to have 1 more valence electron that I'm going to add. So that's going to be a total of 8 valence electrons, all right? So I have just an oxygen and a hydrogen, so obviously I don't have to worry about a central atom this time, so I'm going to bond those 2 together. So there's 2. The hydrogen can't take any more. Remember, it can only have 2 electrons around it, so I've used 2, there's 4, there's 6, and there's 8. Oxygen now has an octet. I've used all 8 valence electrons, but remember, this has a negative charge on it, so when you're drawing an ion, what you need to do this properly, and this is, again, this is a tad bit different from what he does in your book, but what I'm showing you is what most textbooks are doing, so this is what I want you to do. You're going to put brackets around this, and then you're going to put a negative charge up here. In his drawings, he tends to stick the negative charge up there, but I think it makes it a little bit more plain if we bracket the Lewis structure and then put the negative sign up here, okay? What happens if I have a positive ion? So an example of a positive ion would be NH4 plus, an ammonium ion. That's one that you memorized. So let's evaluate this one. So nitrogen is going to have 5 valence electrons. I have 1 for each hydrogen, and there are 4 of them. But because this has a positive charge on it, that means that I've got to take away 1 of the electrons, and so that's going to give me a total of 8 valence electrons, okay? The only possibility for a central atom here is my nitrogen, so my nitrogen is going to be here. I'm going to bond each one of the hydrogens to it. That's going to make 2, 4, 6, 8 electrons, which is how many I had to use. But again, because it has a charge, I'm going to put the whole thing in brackets and put my charge up here like this. All right? You'll probably notice that we didn't get to rule number 6 yet, and we're going to get to that rule a little bit later. We're not going to do it quite yet. I'm going to let you get your feet wet with this part first. Before we close up here today, let's go ahead and go through example 3.1 and make sure that you understood it. So let's get some space here to work that one. All right, example 3.1, what is the orbital hybridization of the central sulfur atom to SF2 and the resulting geometry of the molecule? What is the orbital hybridization in each of the fluorine atoms? Okay, so again, we're going to use our method for drawing this dot structure because in the long run, it's going to be easier for you. So we're going to look at SF2. So the sulfur has 6 electrons plus the fluorine has 7, and there are 2 of them. So 14 plus 6 is going to give me 20 valence electrons to work with, okay? Sulfur is going to be the least electronegative atom here. So I've got my sulfur and I'm going to bond my 2 fluorines to it. So I've used 2, 4. Now I'm going to start filling in with lone pairs. 6, 8, 12, 14, 16, 18. Did I miscount? 2, 4, 6, 8, 10. Ha, I can't count. 12, 14, 16, 18, 20. Okay? Really helps to be able to count by 2s. You'd think I'd be able to do that by now. Okay, so anyway, here's all 20 valence electrons, and so you can see that I just have these singly bonded to each other. Okay, so that was a pretty easy dot structure to draw as long as you can count right. It did ask us what the hybridization was, and so if I look at the central atom, it's pretty easy. All I have to do is count how many items are around it. 1, 2, 3, 4. And so my sulfur is going to be sp3 hybridized. The fluorine is also has 1, 2, 3, 4 electrons around it, or 4 items around it. So it's also going to be sp3 hybridized. What's the shape of this molecule going to be? Well, this is, because it's sp3 hybridized, technically it would be tetrahedral, but because these have been replaced with lone pairs, that alters the geometry just a little bit. And so again, hopefully this, you recall this from your first year course, this is actually going to be a bent molecule because these lone electron pairs are going to shove those fluorine atoms down. Lone electron pairs tend to be hogs and they want more space, and so they're going to take more space and they're going to shove those electron pairs down so that they're not going to be 180-degree angles, and that's why the molecule is going to be bent. Okay. The next thing that he asks us to do is a formaldehyde molecule, CH2O, and wants to know what the resulting geometry is there. So if I do CH2O, let's count up valence electrons. Carbon has 4, each hydrogen has 1, and there are 2 of them. And then oxygen has 6, and so that's going to give me a total of 12 valence electrons. Okay. Once again, this is one of those things where if you got a carbon, it's almost always going to be the central molecule. So let's take the carbon, let's attach a hydrogen and an oxygen. So I've used 2, 4, 6, and then let's start filling in with lone pairs. 8, 10, 12. Uh-oh. I've used all 12, but I don't have an octet around my carbon. So what I'm going to have to do is I'm going to have to take, excuse me, I'm going to have to take one of these, and I'm going to have to make a double bond. So now did I use the right amount? 2, 4, 6, 8, 10, 12. So I've used all 12 valence electrons, and everything has an octet around it. So that all works just fine. Okay. So if I look at the hybridization around each one of these atoms, the hydrogen doesn't have any hybridization because it only has a valence electron in its s orbital, so there's nothing to hybridize. The carbon has 1, 2, 3 things around it, so the carbon is going to be sp2 hybridized, and the oxygen also has 1, 2, 3 things around it, so the oxygen is also going to be sp2 hybridized if I'm looking at each one of them. Looking at that central atom is the one that determines the shape, and so if it has 1, 2, 3 things around it, an sp2 hybridization, that means the shape of this is going to be trigonal. Okay. Finally, the last example that he has there is CS2, and he asks for orbital hybridization and the molecule or the geometry there. So let's do this one real quick. So CS2, count up valence electrons. My carbon has 4, and then my sulfur has 6, but there are 2 of them. And so if I take 12 plus 4, that's going to give me 16 valence electrons. Okay. So once again, carbon's going to be central. Carbon normally is central, but I'm also looking for symmetry, so that would indicate that carbon would probably be there also, so that the molecule is symmetrical. So I've used 2, 4. Now let's start adding valence electrons. 6, 8, 10, 12, 14, 16. Well, I've used all 16, and carbon does not have an octet yet, so I'm going to have to start moving them. So let's say I take this one off and put it there. Now where am I? 2, 4, 6, 8, 10, 12, 14, 16. I've used 16, but carbon still doesn't have an octet. So let's try moving one of these guys and sharing it. 2, 4, 6, 8, 10, 12, 14, 16. Still have 16 valence electrons. Now though, everything's got everything has an octet around it. So now let's look at the hybridization. The carbon, its hybridization, I only have 2 things around it. I've got 2 double bonds, And so therefore, that means that it's going to be sp hybridized because it's got to use one of its sets of p orbitals for this pi bond, and it has to use the other set of its p orbitals for this pi bond over here. Okay, so the carbon is sp hybridized, and the sulfur, both of the sulfurs have 1, 2, 3 things around them. So that means they are both going to be sp2 hybridized. And here, because this is sp hybridized, these bonds are going to try to be as far away from each other as they possibly can get. And so that means that this molecule is then going to be linear, which does go along with sp hybridization. All right, that was a lot of examples, but hopefully it helped you to see exactly what you're going to be doing, gives you, hopefully you're feeling comfortable with how you're going to start putting these things together. And so now I'm going to let you go practice.